Okay, hello and welcome to example sheet 3, question 7. I'm just going to quickly pick out a few key points from the question. Neglecting the effect of the diffuser. In the exam you might have to consider the effect of the diffuser, so just be aware of that. But in this particular case we're going to neglect it, and we're also going to disregard the slight increase in mass at the engine exit, as well as the inefficiencies of the engine components. We're asked to determine the force that must be applied by the brakes to hold the plane stationary. Okay, we're going to solve for the variable specific heat. So we're going to be using table A17, and it's also important to note that the kinetic energy is not negligible at the nozzle exit. Okay, so as I always suggest, it's always worth drawing a TS diagram. Now, since we're neglecting the diffuser, we have a straight through point here to here, isentropic process from points 1 to 2. No need to consider the diffuser. Of course, this is the work in from the compressor. This is rising up to point 3. Work's done by the turbine. Since we're assuming no inefficiencies, this process is isentropic. And of course, then this is point 4 and point 5. Point 4 to 5 is the nozzle. And of course 5 drops down to 1. This is Q out. And this is Q in from point 2 to 3. Since the plane is stationary, the brake force is equal to the thrust force produced by the engine, and the thrust force can be expressed, if you check the data sheet, as the mass flow rate times by the velocity at exit minus the velocity at inlet. Since it's stationary though, we know that velocity at inlet's 0, so we're interested in finding the velocity at exit, which of course is V5. Having found this, we're then able to calculate this thrust force and hence the braking force. We're only given values for point 1, so we're going to have to start with these values and work our way around the diagram in order to find this V5 value, and that's what we need to know. Okay, so starting at point 1, T1 was given in degrees centigrade. Converting that to Kelvin will give you 300K, and using table A17 you'll find that H1 is equal to 300.19 kilojoules per kg, and of course PR1 is equal to 1.386. Now of course, moving around the diagram, PR2 over PR1 is equal to P2 over P1, and P2 over P1 we know is equal to 12. So simply rearrange this. P2 is equal to 12 times PR1, 86, and that will give you a value of 16.63 for PR2. This is the isentropic point, but since the inefficiencies are being ignored, it can be used. So finding Q in, we know Q in is equal to the mass fuel flow rate times the calorific value. And these values are given, so it's 0.2 kilograms per second times 4 to 42,700 kilojoules per kg. Of course, cancel out the units, and that will give you a value of Q in equal to 8540 kilojoules per second. Now we want to find this in terms of kilojoules per kg of dry air as opposed to kilojoules per second, so we're going to divide this by the mass flow rate. So large Q in over mass flow rate is equal to 8540, which we just calculated, kilojoules per second divided by the mass flow rate of 10 kgs a second, and of course we now have 854 kilojoules per kg of air. So this is Q in, this is the heat added during combustion. Now, since we know, looking at this region of our TS diagram, Q in is also in fact equal to H3 minus H2. We just calculated Q in. H2 can be found here. Since we know PR2, we can use table A17 and we'll find H2 is equal to 610.65 kilojoules per kg. Of course, interpolation is what you would have needed to do to find that value, and that is covered in earlier videos. You can find it in example sheet 2, question 1, refrigeration, amongst other examples. Okay, so now we know H2 and we know Q in. We can just rearrange this to find H3 is equal to H2 plus Q in, and just plugging in the values, 610, 65, 854 is equal to, gives a value of H3 equal to 1464.65 kilojoules per kg. Now interpolating this value using table A17, we can find the value of PR3, which is equal to 396.27. Now remember the jet propulsion cycle, the turbine is just to drive the compressor, so we know that W comp in is equal to W turbine out. And looking at our diagram here, of course our comp is represented by this and our turbine is represented by this, so we know that H2 minus H1 is equal to H3 minus H4, and rearranging this equation you'll find H4 is equal to H3 minus H2 plus H1, and subbing in the values. So that gives a value of H4 equal to 1154.19 kilojoules per kg. Okay, so now looking at the nozzle and interested in finding H5, well, in order to do this we can find PR5. So if we find PR5, and of course PR5 over PR3 is equal to P5 over P3. So rearranging this, PR5 is equal to PR3, which we previously calculated, which is shown here, times by P5 over P3, which is of course the inverse of the pressure ratio, so it will be 1 over 12, and subbing those values in, will give you a value of PR5 equal to 33.02. Interpolating table A17 now will give you a value of H5 equal to 741.19 kilojoules per kg. Therefore now for the nozzle, when we consider the energy balance, H4 plus V4 squared over 2, we know that goes to 0, is equal to H5 plus V5 squared over 2. Of course we're interested in V5, we know H5 and we now know H4. So rearranging this equation, times 10 to the 3, which is of course, this is very important because we're interested in having it in joules, and working that out will give you a value of 908.9 0.9 meters per second for V5. Then finally, returning to our original equation here, we now have this value, we know this value, so we can calculate the thrust and hence the brake force. So it's just a matter of subbing those values into the equation, and that will give you a value of 9,089 newtons. Thanks.